Okay, so what I hope I'm doing here, I'm going to try to share my desktop. First of all, I'm my screen share. Okay, here we go. Select a window to share, and I'm just going to do full screen. Start screen share. Whoa, and there it goes. So I'm just going to minimize that guy. I think I'm sharing my screen. Okay, so here we are. It's early January 2015, and what I want to do today is just post a little video here on YouTube that helps you folks out there, mainly my energy technology students, understand the difference between energy and power and link those with the concept of time. So as you probably know, I'm the director of the energy technology program here at Missoula College, and one of the courses we teach is NRG Y 101, and it's critical that students understand what the difference between energy and power are very, very early on in the course. So I'm going to use my notepad, and this is just Windows Journal, and I've got a bamboo pad here with me. And we'll start kind of difficult with the math, and then go with some examples, and hopefully come back to the math. So here is the relationship between energy. So for energy, we're going to use the symbol E. For power, we're going to use the symbol P. For time, we're going to use just the symbol T, lowercase t for time. Typically, uppercase T is for temperature. So those are the three variables that we want to get straight. In a lot of ways, they're just like, the three variables that you'd see in Newton's equations, like F equals ma, or Einstein's equations, E equals mc squared. This is much simpler than that. So hopefully we can get to the relationship. So there's a couple ways to write this out, or several ways, but there's the two main ways are to think about energy just equals power times time. Another way that people typically write it is that power equals energy divided by time. And so typically we think of time as something that we cannot affect, unless we're doing something relativistic, or not speeding up or slowing down time, the clock keeps ticking. So that's why we usually keep energy or power on the left-hand side of the equation. So typically there'll be a scenario where we know what the power rate is, we'll know how much energy we have, and those two things will be on the right-hand side of the equation. So if we know how much power we have, we know how much time we have, we'll be able to determine how much energy was used. Or by the same token, if we know how much energy we have and how long we have to do something, we'll then know how much power is required. So those are how energy, time, and power are related mathematically. Now let's go with a couple examples. So energy is measured in a lot of different units, and I'll just give a few examples here. So energy can be measured in the SI units, or the International Standard Units, are joules. We can also measure energy in calories with a little c. We can also measure it in kilocalories, and that's typically with a big C. We can measure energy in BTUs, British thermal units. We can measure energy in kilowatt hours, and there's something to think about here. The kilowatt, as you may already know, the kilowatt is a unit of power, and we can see right off the bat, in fact, right here, when we multiply this kilowatt by an hour, you actually get energy. So that this one little unit that we've written down sort of gives a hint to this top this first equation, where energy equals power times time. So hopefully that's making some sense. And gosh, there are several others, but those are units of energy. Now let's look at power, and this can be measured sometimes in watts. Sometimes it's measured in horsepower. Shoot, what's another good measure of power? Well, those are the two main ones, and watts are the international system, and HP for horsepower is sometimes called the imperial, sometimes called the SAE for Society of Automotive Engineers, sometimes called the English units, although the British, the English no longer use those. But those are the two main units of power that we're going to consider. Okay, and now let's dig one step deeper and look at the difference between units and dimensions. And this is something that if you don't get it right now, just come back and watch it later, because it's kind of subtle. And then we'll get to some examples. Okay, so what I've shown are units. I'll just write units at the top here, with energy on the left and power on the right. And of course, time, I'll just complete that. We just usually measure in seconds, minutes, or hours, days, years, what have you. I think everyone's pretty familiar with how to measure time, or the units of time. Okay, now the next thing we want to consider are dimensions. And so units, as we just saw, are somewhat arbitrary. They are human artifacts, just in the same way that the dollar versus the euro versus the pound is an arbitrary, societally accepted unit for measuring money. Well, we won't get into exactly what money is, but it's something, units that we use for measuring things that we all agree to. And we can agree to the fact that time is there, power is there, energy, but we have different conventions for measuring. Now, we're going to now just sort of delve into some fairly basic physics and how the dimensions of energy and power are derived. So first of all, let me give one example of energy. And we'll just look at potential energy first. So potential energy is some example where you might have some mass, M, sitting on a table, and you're then going to lift this. You could lift it by hand, you could use a forklift, anything, but you're going to have to lift it from one position up to a higher position. And to do so, you're going to lift it through some height that we'll just call h. So you've taken the chunk of mass, and here's just a standard coffee cup. And to get it to a higher position, I had to put some energy into it. I've got muscles in my arm moving this cup up. So now the cup has more energy than it previously had, and I moved it through some distance h. Fairly simple, fairly straightforward. Now, since I'm sitting here in a gravitational field, I'm moving it against this constant gravitational acceleration that we experience. So right here, you can see I have three variables. I've got m, I've got h, and I have g. And so that's one very simple way of looking at energy. So energy equals m, g, h. The more massive the cup is, if I was lifting a bowling ball, and instead it would take more energy. If I were in a heavier gravitational field, like on Jupiter, it would take more energy to lift at that same height. Or if I were going to move it even higher, it would take more energy. So the combination of those three, the more mass, the more gravity, or the more height you have, the more energy it's going to take to move that up. So now let's dig into the dimensions of these three things and see if we can't find out what the dimensions of energy are in fundamental physical dimensions. So height is just another, and I'll put height right here, it's kind of easy. Height has dimensions of length, so I'm going to use big L for length. Mass has dimensions of, that's what the brackets mean, dimensions of mass, and I'll use big M for mass. And then gravity, the dimensions of gravity, if you remember your physics courses, you remember that gravity is measured in meters per second squared or feet per second squared. And that ends up looking like length over time squared. And I've used a big T just to mean the dimensions of time. So if we multiply those together, the dimensions of M, which we said were just M here, dimensions of G, which were L over T squared, and the dimensions of H, which was again L. And so now I'll write the dimensions of energy just equal mass length squared over time squared. Okay, so those are the dimensions of energy. It's mass times length squared over time squared. Now let's look at power. And we'll use that same little potential energy example. And now what I'm going to do is scroll back up and remind you that power is just energy divided by time. So I think everyone can appreciate that if I do this once to go from a height, a lower elevation to a higher elevation, that took a certain amount of energy. If I do it again, it's going to be the same amount of energy. But now you might say, well, what if you did that a little quicker? You went from here to there. Now, it was the same change in energy, but I did it more quickly, and I had to be more powerful. In the same way, you could imagine like a large football player moving. Somebody who's moving much faster is going to be more powerful, or going quicker in your automobiles is going to be more powerful. It might take the same amount of energy to get from point A to point B, but the fact that you did it more quickly means you're more powerful. It's a more powerful system. So let's look at that. So again, if we know that power equals energy divided by time, we can now say that, and let's put some numbers in there. So let's take it up a notch and just go from the algebra maybe into some arithmetic, and let's just say that oh gosh, this thing just has a mass of 1 kilogram. So that's 2.2 pounds, and again it's sitting here. And then let's just lift it a distance of 1 meter, and now here it is at the top. It's still that same kilogram, and this coffee cup weighs, gosh, maybe a quarter of a kilogram. But you can imagine a 2-pound object, a 2-liter soda, for example, weighs about a kilogram. Oh, I'm sorry, no.
Okay.
No, yeah, a 1 liter kilogram weighs about 1 kilogram, one kilogram per liter approximately for water. So imagine your 1 liter soda being lifted. 1 liter being lifted 1 meter, that's 1 kilogram. And gravity again is pointing this way, and it's approximately 10 meters per second squared. And now if we do this, imagine doing this over the course of 1 second. So now I've sort of drawn in a time arrow here. And remember, this is just our mass. This 1 kilogram mass is here. And we're going to move it up here. We're going to move it a height of 1 meter. And if we do it in 1 second, maybe I'll erase that and just say, let's do it like this. T equals 1 second. And again, this is gravity equals 10 meters per second squared negative. So now we can say that the energy, we'll just start with energy, equals again our mgh equals 1 kilogram times 10 meters per second squared, and then h is 1 meter. Let's put some parens around that so that we can see each one individually. There we go. So now another thing to keep in mind is we're going to treat the numbers and the units separately. So all we have to do over here is do a 1 times 10 times 1, 10. And then the kilograms meters squared per second squared. We'll see what that is in a second here. So equals 10 kilogram meters squared per second squared. Now, as it turns out, this is very convenient in international units, is that a kilogram meter squared per second squared is just a joule. So that equals 10 joules. Now, what I said before, I'm going to do this over 1 second. I'm going to do this over 1 second, and I'll use my equation. P equals energy over time equals 10 joules divided by 1 second equals 10 watts. And we already saw previously that the watt is the international unit of power. So again, just to do this simple task to go, and I'm not quite lifting a full meter, but just to lift a 1 kilogram mass 1 meter up in 1 second takes 10 watts. Now, what if I were to do this in 1/10 of a second? Well, much quicker. It would be 100 watts of power. If I did it over a much slower amount of time, if it took me 10 seconds to do that 10 joules of energy, it would just be 1 watt. Now, you might argue, well, okay, but what's going on in your arm? Aren't you constantly supplying energy to your muscles to lift your arm? Well, technically, I am, of course. But if this were a simple machine, it was just a string dangling and pulling, then the rate of power would be slower. Of course, there's the metabolic energy of running my organism here. But if it were a simple machine, you can see how these numbers would work out quite nicely. All right, so that's the difference between power and energy. Another way to think about it, just to complete the analogy, I'll give you one more analogy to sort of hopefully drive the concept home. Is that imagine that you're in a car here, and you're going to drive. Oh my gosh, this car is going to look terrible, but hey, whatever. Dr. Seuss got away with it, so can I. So the car is going to drive some distance, and when it does so, it's going to drive also at some velocity, and it's going to take the car a certain amount of time to get there from point A to point B. Here we are, point A to point B. So I think you are probably familiar with the notion that velocity just equals distance divided by time. And so in this analogy, you should be able to right away see that distance is similar to energy. It's how much of something you have. And velocity is similar to power. It's how quickly you consume that. So just as with lifting the coffee cup, it was the same amount of energy each time, but we expended that energy more quickly, or in some cases more slowly. It's the same thing with the velocity. So you can imagine driving your car more quickly, or maybe you're taking an airplane, you're even faster, or maybe you're just walking, it's even slower. But in each case, the distance covered is the same. It has not changed. And you can loosely tie that in with the whole notion of the first law of thermodynamics, where energy cannot be created or destroyed. Same thing with if you're driving on your commute, and the distance you're going to go is going to be the same every single day, but you might get there faster or slower with a faster or slower velocity, or with a greater or lower energy consumption rate, which means greater or less power. So hopefully that drives home the concept of the fundamental difference between energy, power, and time and their relationship. Okay, so thanks for hanging out, and then I think we're going to stop.